Hi guys, welcome to your lecture number 4. Today we'll be learning about the projectile motion. But first things first, I figured out a way to develop or uh, derive the third equation of motion in the last lecture in a vectorial format as well. So in the last lecture, if you might have noticed, our equations of motion, the first equation of motion, again for projectile motion we will also require those equations of motion, so I'm going to write them again. Our first equation of motion was uh, v vector equals u vector plus a vector t. Our assumptions were this acceleration vector a vector is a constant vector, meaning its magnitude and direction both are constant. The u vector was a constant initial velocity. It has to be constant by its initial, right? And this is the amount of time in between events when the initial velocity was u vector and the final velocity became v vector. So that is the amount of time which the body spent in between going from initial velocity u to final velocity v vector at a rate of a vector, uh, at a rate of an acceleration a in its vectorial format. So this was our first equation of motion. Our second equation of motion was s vector equals u vector t plus half a vector t squared, and we said, okay, if we look it through, then our again this u vector is the initial velocity, a vector is the acceleration, which is constant in this assumption. T is the amount of time which it is spent in between going from initial velocity u vector at a constant rate of a vector. It could be positive, it could be negative acceleration or retardation depending on the sign, and the amount of distance the body has traveled in time t, starting at u vector and accelerating at a vector, is going to be your s vector. So this is for displacement. So the third equation of motion we wrote as v square equals u square plus 2as, where there is no time term. What we did was we said, okay, this is an scalar analog of the third equation of motion, where v is the final velocity, u is the initial velocity, a is the amount of acceleration which the body experiences while going from its initial state at velocity u unsigned to velocity v unsigned, and it travels a distance of s in doing so, a displacement of s in doing so. So with all these things over here, I was just thinking about if it will be a possibility for us to arrive at this third equation of motion in a vectorial format as we did for other equations of motion. We might have uh, a scalar equation still, but can we arrive at from a dot product scenario? I know it's in class 11th. Nobody learns about dot product at this early stage in their class 11th, but the courses have changed quite a lot, and generally in your physics books, there will be some initial chapter about dot products. So anywho, let's go with the notion of first and second equation of motion. Over here, what we arrive at is that if you write the amount of time, you can write you know the first equation. You can rearrange the first equation of motion. Sorry, you can rearrange the first equation of motion to get your acceleration in terms of v vector minus u vector divided by time. I just divided this entire first equation of motion first by the amount of time t, which is a scalar quantity, and then I took this u vector, and then I subtracted u vector from both the left hand side and right hand side of the equation in order to arrive at a vector. Or you can do that you have to do that first, that you subtract u vector from the left hand side and right hand side of the equation, and then divide the equation thereafter by time in order to arrive at this rearranged equation for getting the acceleration vector. Okay, so once you get that, now we'll throw this in equation number 2. um, so we'll get s vector equals u vector t plus half v vector minus u vector divided by t times t square. We get u vector times t plus half v vector minus u vector times t. We write that as v vector plus u vector divided by 2 times t. Now again, so this is what we get for getting this s vector quantity out here. Now what we have to kind of remember is this is what we are getting for this s vector value, right? So in order to obtain this equation from here, what we might need to do now is to again look at the first equation of motion. In order to look at the first equation of motion, we have to be very careful in rearranging for the time part. So how would we like to do that? That would become very we have to be very careful in doing so. So uh, yeah, so what we are going to do over here is that let's say we get equation 3a. We will do a dot product of this equation 3a with your a vector. So a vector dot s vector will be a vector dot v plus u divided by 2 times t. Now this a vector is nothing but v vector minus u vector divided by t. So we'll write this a vector again as v vector minus u vector divided by t dot v vector plus u vector over 2 times t. The t and t will cancel and we'll get a dot s as v vector minus u vector dot v vector plus u vector. So if we distribute this multiplication of vectors over here, distribute this dot product of vectors over here, we get v dot v as the first term, the second term will be v dot u, the third term will be minus u dot v, and the fourth term will be minus u dot u. Now remember, for dot products, the uh, the v dot u or u dot v, the order does not matter in terms of the dot product. So v dot u and u dot v will cancel with respect to each other, giving us v dot v minus u dot u. And this v dot v, you can write it in terms of the magnitude of the final velocity squared minus the initial velocity squared equals a dot s. I forgot the half term over here, so I would request you guys to keep track of that if you could. So what we'll arrive at is that mod of v square minus mod of u square equals 2a dot s. So now, apart from velocities in the apart from motions in the same direction, even if the motions are not in the same directions anymore, if the acceleration vector is a constant, we can easily get the final velocity in terms of the initial velocity using this particular concept over here. Okay, so this is what I wanted to impress you upon, and this is my third equation of motion in vectorial format. The thing is, although it's in vectors, you can see that there are dot products involved and the magnitude of velocities is squared. So this is no longer a vector equation. I mean, it has vector valued quantities, but ideally speaking, after dot product, vectors tend to produce scalars. So it's still a scalar equation, but we have everything which we want to in order to solve for vectorial u, v, and a and s together in this third equation of motion. So thereby we'll go to our intended understanding of projectile motion. So for that, what we would like to do today is just go through the concept of projectile motion using these three equations of motion. I'll just write those three equations of motion for you on the side for you to refer from as we go along in this lecture. And again, if you have any doubts or if you have any questions or if you are trying to solve a book like Irodo or Kroto, just ask me questions and we can go from there in terms of your doubts. So anywho, we'll jump into the projectile motion. Which is the main crux of lecture 4, which we are trying to do in here. Again, my equations of motion all in vectorial format. B vector equals u vector plus a vector times t. I'm not going to tell what these quantities over again and again. I think now all the assumptions are known. The initial and final velocities, the time it takes to go from initial to final state, everything is known. The displacement, the second equation is about displacement, those kind of things are known now. Okay, so let's start with the projectile motion. So what happens in a projectile motion is that you throw like if you have seen during Olympics, there are people who throw shot puts, and they generally tend to throw it at an angle with respect to the ground, and then that stuff what they're carrying hits the ground at some distance away from the person who is throwing it. So that distance is called range in the horizontal direction, and in the vertical direction, the amount the maximum height this shot put goes to is h. And basically, what we are interested in is that if I have been provided with a velocity v or u for that matter, with an initial velocity u at an angle theta, what will be the maximum height of the shot put I can achieve, and what is the maximum distance from the initial place from where I'm throwing that object will hit the ground. So these are the two major questions of interest. Also, the question of interest is for how much time this entire ball will be in the air, for that matter. So we'll start solving these questions uh, in a very planned manner. So in order to look at projectile motion, I would say if you do a two-dimensional analysis, it will be very, very complex. Instead, what you can look at is a one-dimensional analysis. So let's say that there is a stream of light um, which is which you are flooding from the left-hand side of the person, and then basically you're recording how the ball is going up and down. So in order to get the recording in the vertical screen, what you will see is that the velocity will no longer remain u. It will be it will have its components in the horizontal and vertical direction. The horizontal component will be u cos theta, and the vertical component will be u sin theta, and then you can forget about the initial velocity u once you have the u cos thetas and u sin thetas. Okay, so you will start with the velocity of u cos theta. You will hit here when the velocity will become 0, and then you will come back. So basically the 1D analog of this two-dimensional motion will look like this, right? So how to do this? So again, it's kind of simple. What we are looking at is the is the instant when velocity will hit its zeroth, when velocity in the upward direction will become zero. At the point when the velocity in the upward direction will become zero, that will be the point when the shot put or the object will achieve its maximum height. So in order to then solve for this problem, now you can forget about your 2D motion, only as far as this vertical motion is concerned. You don't need to worry about this. What you need to worry about is this picture where you're throwing a ball upwards at a velocity of u cos theta, and then that velocity becomes zero in its final state when the object achieves its maximum height with respect to ground or from the ground. So how do you solve for this problem? You can do it in terms of the third equation of motion from here. V mod square is initial velocity is u cos theta j cap. This is zero, so it doesn't have a direction. This one has a direction, but I'm going to take its magnitude anyways. And then my acceleration due to gravity g vector is minus 9.8 j cap, but my height is going to be traversed in the upward direction, so that is plus h j cap. So minus 9.8 j cap as far as acceleration part is concerned, because it is in the opposite direction when it's facing downwards when the ball is moving upwards. So that is minus 9.8 j cap darted with the height in the positive j cap direction, and let's say that the height it achieves is capital H j cap, right? Which is also the quantity here. So when we do all this, so since we are interested only in the magnitude of this, so j cap will not have any significance because it's a unit vector. We'll get u square cos square theta equals 2 times minus 9.8 times h, and with a negative sign here because that is outside of the value. So the j dot j is the dot product of j with respect to itself is 1, so we can forget about that. Now the negative and negative will cancel. Your h will come out to be u square cos square theta divided by 2 times 9.8. Or if you have not converted your g into 9.8, it will be simply u square cos square theta divided by 2g. So that will be the maximum height this projectile can achieve in its course of motion from initial position to the final position. Now the other important interesting concept is how much is the range of this projectile. Okay, so in order to find out the range of this projectile, you will throw a stream of light in the negative j direction, and then basically you will see a shadow of this ball moving in the horizontal direction. But remember, in the horizontal direction there is no deceleration factor. In the vertical direction, when we were throwing the ball up, there is a deceleration factor due to Earth's gravitation. But in the horizontal direction, there is nothing like that present. So what we can do for that case, we can throw in the second equation of motion, which will become S vector equals u vector t plus half a vector t square. There is no acceleration in the horizontal shadow direction, so that is 0. Now we are only interested about S vector equals u vector t. My S vector is r vector, and my initial velocity in the horizontal direction, So if I have u vector in the horizontal direction, it will be u cos theta. Already we know the velocity in the vertical direction from there, it's u sin theta. So your r vector is u cos theta I cap times t. But we don't know the amount of time it took to go from its initial state to final state. So that time could be achieved again from this image when we do not use this third equation of motion, and I am assuming that you have taken notes of how we calculate the maximum height. If not, I'm going to give you 1 minute, but we'll use this vertical motion scenario and use the second equation or the first equation of motion in order to achieve the amount of time it required for the for in the vertical screen for the ball to go up and then come down, or the body or shot put to go up and come down. Okay, so here is your minute when you can actually take more notes uh, on the usage of third equation of motion in the vertical component of projectile motion scenario. Again, I would like to remind you guys, I'm doing this for fun, but I'm really passionate about physics as it appears, as we see very challenging problems in IIT JEE examination. This is just out of my passion, and I want to help you guys in any manner I could. I know that now getting selected in IIT JEE is a very high function of whether you have the financial ability to avail a tutor. Um, so, so I just want to do it for free for those people who cannot achieve, who cannot go to, tutors who charge extraneous amount of money, or for people who just want to get a second opinion about how they can you know looking this as a refresher course for their preparation. So anywho, I think that's the philosophy behind why I am taking this course. So I'm not going into detail about that. So yeah, so in this problem, let's put in uh, let's put in the first equation, and we can solve it both using the first equation of motion or the second equation of motion to get my time as the ball went up and then came down. But I would like to use the first equation of motion over here. So there are two time instances involved, one for going up and then one for coming down, right? So but the height will remain the same in both the scenarios. I think the height formula which we got was u square sine square theta divided by 2g, right? So I think it's wise to use the second equation of motion. So as far as second equation of motion is concerned, we have s u vector t plus half a vector t square. We know this quantity uh, as as the ball is thrown up. So this is the first component of the vertical motion when the ball is only traveling in the upward direction. So that time is going to be t1 when I throw the ball or body or shot put up, uh, or its shadow in the vertical screen up, and it achieves a velocity v of 0. Okay, so problem I have the height getting traveled in the plus j direction. So this is going to be u square sine square theta divided by 2g in j cap direction. Your initial velocity is u sine theta j cap t. Your acceleration due to gravity is in the negative direction. So that is plus half minus g j cap t square. And using this we can solve for this problem, right? Or you can solve it using the first equation of motion, because this is going to become a quadratic. So if you look at the first equation of motion, that is v vector equals u vector plus at, your final velocity is 0, your initial velocity was u sine theta j cap, your acceleration is minus g j cap, and your time is t. For the first part, when the ball is only traveling in the upwards direction, so your time t1 is u sine theta, because everything is in j cap direction, you can take it away. Similarly, when you again solve for the time when the velocity is, the initial velocity is 0 and then it has to travel the h distance, you'll get your second time. By symmetry over here, you will get that time to be also u sine theta over g. So your total time will be t1 plus t2, which you can incorporate here for your range of the shot put. So that is going to come as u cos theta I cap times t1 plus t2. Since by symmetry both of them were the same quantity, so we can write it as 2 into t1, which will become u cos theta I cap times 2 times u sine theta over g. So my range will be in the positive x direction, 2u squared sine theta cos theta over g, or we can simplify it, since sine 2 theta is 2 sine theta cos theta, you can simplify it to write it as equals u squared sine 2 theta over g I cap. So that is the range which the projectile is going to cover. So we know the height, the total amount of time is 2u, is t1 plus t2, which is 2u sine theta over g, and then the range of the projectile, which is r, in the positive x direction. So with that, this concludes the easiest way of looking at regular projectile motion. We'll also look at some more complex cases of projectile motion in our next lecture. So till that time, I would like to say thank you for your time, and hope we can solve some more problems together. So I'll look into that as you give me more and more problems in the comment sections to solve that. This is both for your benefit and my benefit, as I want to be in the you know in the flow of solving these kind of problems, um, and it might also help you out if you can look at some other variation of that problem or some other way of solving that same problem. So anywho, our next lecture will be more complex projectile motions, which will be uploaded soon, after this gets uploaded. Let me know what you think about all these videos, and if there are ways of improvement for me to get you a better lecture. Thank you, and with that we conclude lecture number 4 in this series. Thank you.